This is a kind of semiconductor which consists of N-type and P-type semiconductor. And at this point, N-type and P-type semiconductor makes junction. Then what is N-type and P-type semiconductor? N-type semiconductor is rich with electrons because of the ionized donor, so the Fermi level of it is higher than the intrinsic Fermi level. On the other hand, P-type semiconductor is rich with the holes because of the ionized acceptor, so the Fermi level of it is lower than the intrinsic Fermi level. In p-n junction diode, we should connect these two different energy bands, and the first step of the connection will be to make the Fermi level constant to express the thermal equilibrium condition. So draw the Fermi level constant first, but nevertheless the characteristic of each semiconductor must be kept. So the gap between the conduction band and valence band to Fermi level should be kept. But anyway, we are connecting these two different energy bands. So at the center of the junction, each band should be bended to be connected. So the bending of the energy bands makes the built-in potential. In this energy band, we can divide two different sections, the neutral region and the depletion region. In neutral region, the mobile carrier and the dopants combine one by one, so there's no charge. But in depletion region, each different mobile carriers combine each other, so the dopants left as the fixed charge. This shows the change of the energy bands by the direction of bias. At first, let the p-type as anode and n-type as cathode. And if we give the forward bias to the energy band for the p-n junction diode, the bias make the built-in potential smaller than before. So the electrons in this energy band can move easily to side by side. But if we give the reverse bias, it makes the built-in potential much bigger than before. So the electrons cannot move easily in this band. But if we give too much reversed bias to the band, the energy band bends extremely, so the electron at this section can be moved to another section because of the electron's wave-like property. We call it electrons tunneling. And this tunneling can make a current in this diode. So this is the IV curve for the bias. At the forward bias region, the current increases exponentially by the voltage. But at the reverse bias region, the current is almost zero at this region, but after we give a huge amount of voltage reversely, the current increases. Actually, this decrease in this graph, but the amount of the current increase. So yeah, the current increases a lot after we give the huge reverse bias. This is energy band of Schottky diode. The PN junction diode consists of P-type and N-type semiconductor, but the Schottky diode consists of metal with the N-type or P-type semiconductor. Anyway, same as the P-type PN junction diode, to express the thermal equilibrium condition, we should draw the Fermi level constant. But in metal, we do not use the word Fermi level. The metal has the work function of its own. So make the work function of metal and the Fermi level of N-type or P-type semiconductors constant, and then draw the energy band of the N-type semiconductor and P-type semiconductors each. But same as before, we should keep the property of its own. So the gap between the valence band and conduction band to the Fermi level should be kept. So at the junction of the metal and the semiconductor, the band of the semiconductors will be bended at this point.